before the break, we mentioned simply supported beam. I tried to apply our upper bound theorem and lower bound theorem to analyze a simply supported beam. We learned that both procedures can help us to evaluate our collapse flow. Let us proceed further. We try to consider statically indeterminate beam. Indeterminate means the number of reactions is more than the number of equations, so that you cannot find out the reactions easily, directly. We would like to know the strength, the collapse law for indeterminate beam. Statically indeterminate beam. Well, the plastic hinge location normally is not that obvious as compared with simply supported beam. You may need to have some structural sense to observe where to have your plastic hinge. One skill is that you may roughly sketch the moment diagram. Don't need to know the exact value, just roughly sketch the moment diagram. It will help you to identify the potential position, the critical positions where you have plastic hinge. The number of plastic hinge needed for plastic collapse is 1 greater than the degree of static indeterminacy. We just mentioned this term before, static indeterminacy. Static indeterminacy means the number of reactions minus the number of equations. Just like fixed end beam. For fixed end beam, under loading, say for example here, for fixed end beam under loading, you have totally 4 reactions. It seems that you have 4 reactions over here, right? And you have 2 equilibrium equations, one for vertical force, one for moment equilibrium. So when you calculate the static indeterminacy, static indeterminacy is equal to 4 minus 2 equal to 2. Maybe I call this n, right? N is the static indeterminacy. 4 minus 2 gives you 2. So according to the statement right here, the number of plastic hinges required to make the structure collapse is equal to the number of degree of determinacy, the degree of indeterminacy plus 1. So the number of plastic hinge required, it seems that it's equal to n plus 1 equal to 3. 3 plastic hinges can make a fixed end beam become unstable, collapse. You can use this kind of idea to estimate the number of hinges required. Right. Firstly, calculate the indeterminacy, and then plus 1. That is one skill you may use. But personally, I seldom use it. Personally, I just add hinge continuously on the structures. Say, for example, I add hinge on the structures. After adding 1 hinge, it's still stable. And then I add another. After adding 2 hinges, it's still stable, right? After adding 2 hinges, it's just like a simply supported beam. For simply supported beam, you can add 1 more hinge. For myself, I normally add hinge continuously until I observed that there are some unstable pattern occurred. I seldom memorize this kind of rules because I think that is not quite maybe sometimes it's useful, but I seldom use it. Anyway, you can firstly use your scale to predict the location and the number of plastic hinges, and then you can use the collapse mechanism. You can use upper bound theorem or lower bound theorem to find the collapse flow. For indeterminate structures using upper bound theorem, using the energy is normally more easy. Talk about the behavior first. Instead of talking about the calculation here, show you again the behavior. And also it will affect our design procedure a little bit. For a fixed end beam under uniformly distributed load, at the beginning, when the load is small, everything remains elastic. There's no plastic hinge when the load is small. When the load increases gradually, the plastic moment, the moment diagram, the moment value will increase when the load W increase until when the location of maximum moment reach the plastic moment. For fixed end beam under UDL, this is the shape of the moment diagram for a fixed end beam under UDL. Maximum moment occurred on the two sides of the fixed end beam. The value is equal to WL squared over 12. The moment at the middle is smaller, over 24. So you can see that when the load W increases gradually, the first point reaching, the first plus hinge that will form in the beam is actually the end of the members. It will form right here and right here because the moments are maximum at these 2 points. After formation of the two plus hinges, it's just like a simply supported beam. For simply supported beam, it can take one more hinge before collapse. So finally, you have 3 hinges, 1, 2, 3. In terms of the moment diagram, you can take a look on the right-hand side. Well, after formation of the two plastic hinges on the two ends of beam, and you can see that the two ends yielded fully plastic, but the middle remain elastic. The moment at the middle is still smaller than the maximum moment, smaller than the plastic moment. So in theory, you can also add more loading. You can add more loading so that until the middle point is also reaching the plastic moment. In terms of design, in terms of structural design, that means you can utilize this kind of plastic hinge formation to increase the utilization rate of this beam. Okay, after formation of plastic hinge, it doesn't mean collapse, just like here. After formation of the two hinges on the two sides, it doesn't mean collapse, it's still stable. We can still utilize the middle region to take the extra loading. So the final collapse load is bigger than W1. You can also utilize the beam at the middle to take the loading. Then you can fully utilize the whole beam. Okay. Actually, you have seen this kind of idea before when you learn ROC beam design or ROC slab design. When you learn ROC beam or ROC slab design, you have seen one term called moment redistributions. Moment redistribution is something related to the concept that I mentioned before. By using the plastic rotation, you are allowed to redistribute the loading to the remaining region, which remain elastic, so that you can fully utilize the whole beam element instead of just relying on a few critical positions. This is so-called moment redistributions. Suppose you have a beam, fixed end, or continuous beam. Okay, assume that the beam have equal bending capacity in both mid-span and support, so that you have every section you have the same plastic moment. And assume that the beam has sufficient rotation capacity. For steel beam, it's always normally okay for steel beam, unless you have something like local plate buckling. Do you still remember what is local plate buckling for steel beam? Although this module is not related to design of structure, but I think it's good to understand and remember this kind of basic things. Right? You have learned ROC design and steel design. For steel beam, we have something called local plate buckling. The flanges or the web may buckle locally due to large axial force or large bending moment. When you do the steel design, you have to conduct one thing called section classification to classify the steel section to either class 1, class 2, class 3, or class 4. Class 4 means a section with severe local plate buckling issue. If the member has the issue of local plate buckling, then the rotation capacity is normally small. Then you cannot utilize this kind of plastic rotations. For ROC beam, it relies on your reinforcement detailing. If you follow some very strict detailing rules, say for example, if you provide sufficient reinforcement, you fulfill some reinforcement ratio. The ratio is not too large, less than 2.5%, and then you have sufficient confinement, something like stirrup at the beam end. Right? You can for reinforced beam, you need to provide some longitudinal bar. You have to satisfy some steel ratio requirement, and then you have to add some stirrup. We call it confinement on the two sides of the member. If you have this kind of very strange reinforcement design rules. Then the beam section is also capable to rotate with large volume, even though it is RC structures. We normally think that RC is something like brittle material, right? But in fact, it can be ductile as long as you fulfill some special detailing rules. Now, anyway, I suppose we have adequate rotation capacity, no matter steel or RC. Then you can utilize this kind of vast rotation to make your design more economic. Because just like the previous example, you can utilize not only the end, but you can also utilize the middle part to take the loading, right? Okay. So the overall reinforcement usage will be smaller and make your design more economic to do so, because you utilize the whole beam, not just a few positions. And then you can reduce the reinforcement congestions. If you just design for a few critical sections, the beam end, you may need to add many longitudinal bar, many stirrups at the two sides. It will make the steel bar overlapping with each other. That's quite difficult to apply in practice. So using moment redistribution can also reduce this kind of issue. Okay, some discussion to correlate the concept in this chapter to some practical situations. Go back to calculations. Well, I would like to consider this beam, one span beam. One end is fixed, the other is a roller support. We have one concentrated load at the midspan. In this example, you're asked to calculate the collapse load, P, using both upper bound and lower bound FIVM. In this example, I would like to compare these two FIVM again. And this time, I believe that you will see the beauty of using upper bound FIVM as compared with lower bound. Firstly, how many plastic hinges will form? If you want to apply upper bound FIVM, you have to try your best to predict the failure mechanism. You can using the idea that I shared with you before. You can add plastic hinge continuously at different critical positions. Normally, for a beam under concentrated load at the midspan with some fixed end like this, normally the critical positions are the fixed end and the location of the point node, right? That means point A and point B in this example. Say for example, I add one plastic hinge at point A, for example. After adding one hinge at point A, it becomes something like a simply supported beam. For simply supported beam, you can add one more hinge, probably at the middle, point B, right? Then it becomes unstable. You can apply upper bound FIVM directly based on this failure mechanism. The upper bound FIVM is quite straightforward, I think. You can find out the internal work, find out the external work, set them equal, and then find out the collapse load. Quite easy. In case if you want to use lower bound FIVM, then you have to try your best to draw the moment diagrams. You may draw the moment diagrams and then use the moment diagram, set the maximum value equal to the plus moment, and then evaluate the loadings. It takes you a longer time. Anyway, how about the solutions? Firstly, I showed you the elastic moment diagrams. This diagram is not compulsory when you want to use upper bound FIVM. Okay, this diagram is not necessary when you use upper bound FIVM. I put the diagram here just let you know the critical positions. Fixed end and the point node location, because you can see that the moment at these 2 points are relatively large as compared with the other positions. So it seems that my previous discussion, adding plastic hinge at point A and point B are reasonable, right? You can use the moment diagram help you to predict the critical positions, but not compulsory when you want to use upper bound FIVM. Okay, let us have a look how to apply upper bound theory on this problem. One end fixed, one end roller support. As mentioned before, there are 2 hinges because the hinge is the beam is statically indeterminate to the first degree. The degree of indeterminacy is 1. So according to the previous statement, the number of plastic hinge required is equal to 1 plus 1 equal to 2. Or you may add hinge continuously until you see some unstable mechanism. One hinge formed at point A, the other hinge formed at point B. This is our collapse pattern, collapse mechanism. Based on this collapse mechanism, you can find out the external work, find out the internal work, and then equate the two things together. External work. Maybe I'll add some step here. External work is mainly due to the external force. We have only one external force, PC, in this picture. PC times the displacement, delta, give you external work. How to find out delta? I use the previous concept, arc length. You can imagine that there's a big circle over here. And then you can use arc length to evaluate what is delta. Arc length is equal to the radius. The radius is equal to length over 2 times theta. When you apply upper bound theorem, you don't need to know the exact value of theta. Okay, when you apply upper bound theorem, you don't need to know the exact value of the rotation because we can't calculate. You can simply let them with some symbol. Normally, I use theta, alpha, beta, this kind of grid number, a grid symbol. Finally, the symbol theta will be eliminated in the equation, so that set value is not important. Work done due to external work is equal to PL over 2 theta. Then what about internal work? Internal work is equal to the work done dissipated at the location of plastic hinges. You have 2 plastic hinges this time. So suppose you have 2 internal works. One is at point A, the other one, point B. At point A, the plastic moment is MP. My plastic moment always the same. Suppose the beam is homogeneous along the whole sections. MP. The rotation, you can see clearly the rotation is equal to theta. So MP theta is the first plastic moment. Plastic work at point A. Plus the one due to the plastic hinge at point B. At point B, the plastic moment is also equal to MP. Plastic moment depends on only the section and the yield stress. If they're the same, then it's also equal to MP. MP times the plastic rotation. The plastic rotation originally is a straight line, but it's now under bending of 2 theta. So the plastic rotation is equal to 2 theta. This is the contribution at point B. What about point C? Point C is not a plastic hinge. Point C is a real hinge, roller support. There's no moment at point C. There's no moment at point C. It is a real roller support, a real hinge. So there's no any plastic work at point C. Don't need to consider point C. Point C is not fixed, okay? Point C is not fixed. Nothing at point C. So when you read the solution, there are only 2 terms. One is at point A, the other one is point B, no point C. Once you have the expression for external work and internal work, you can equate their number. Then you can get our energy equation, virtual work equations. You can see that theta appeared on both sides of the equation. You can eliminate theta. So theta, the value is not important because you can eliminate theta at the end of your calculations. So it seems that PC is equal to 6 MP over L. According to upper bound theorem, it just takes you 2 steps you can estimate the collapse load. Okay, 2 steps can help you to estimate the collapse load. There's no need to know the elastic moment diagram. If you need to draw the moment diagram, I believe that it may take you maybe 30 minutes or 1 hour. It takes you much longer time. So when the problem getting and more complicated, you can start to see the advantages of using upper bound theorem. But you need to develop your skills how to predict the location of plastic hinge. And what about lower bound theorem? For lower bound theorem, you need to go for a long journey because firstly, you have to try your best to get your moment diagram. You need the elastic moment diagram. You can use for diffraction formula, you can use moment distribution, or you may use Stewart's method. Try your best to sketch, to obtain the moment diagram. You have to also know the value at different positions. I give the moment diagram at the beginning. Right here, I give you the moment diagram at the beginning on page 12. And when you read the values, you can see that maximum moment occurred at point A. That means plastic hinge will form firstly at point A. Okay, plastic hinge will form at point A. So this value, MA, is also equal to MP. Maybe negative sign. The value is equal to MP. This is one condition we have from the moment diagram and the yield requirement. This value is equal to our plastic moment, negative. And then using the moment diagram, you can express the moment at point B in terms of MA. You can express MB in terms of MA using the moment, plastic moment. We try to express our moment at different positions using MP. MP plastic moment is a well-defined value. MP is equal to the yield strength times the design, times the plastic modulus. So MP is a well-defined numbers. Depends on the cross sections. So we have some extra conditions for this problem. Then what next? Next, we have to apply our equilibrium equations. We apply equilibrium equations. The first picture shows you the overall structures A, B, C. And you have moment, you have plastic moment on the left, right? Point A, we have plastic hinge. You have reaction. We have point node at the middle. We have at the roller support, point C, we have one reactions. The right-hand side picture. The right-hand side picture shows you the force diagram only at portion BC. Only at portion BC. At this point, the moment is equal to 5/6 MP according to the previous page here. We know the moment at this point. And then we have shear force at point B. We have reaction at point C. So at this time, you can set up moment equilibrium. And you can also set up force equilibrium. Combine two equations, you can find out RC, reactions, and also you can find out PC, collapse load. So lower bound theorem firstly rely on the moment diagram, and then to utilize the plastic moment, express some moment in terms of the plastic moment. This will give you some extra conditions. Using the extra conditions, you can use it to solve your equilibrium equations. Okay, the value is smaller than the upper bound theorem. Lower bound theorem gives you the lower bound. More conservative, but more difficult to apply. The picture right here shows you a few steps, but in reality, you have to go through a long procedure to get this moment diagram. But anyway, this shows you how you may use lower bound as well. Okay. So after comparing lower bound and upper bound theorem, you can see that upper bound theorem is much more straightforward as compared with lower bound theorem. Let us apply upper bound theorem again for this fixed end beam scenario. We have fixed end beam, both ends are fixed. we apply upper bound theorem to solve the problems. Here, you don't need to use lower bound. To use upper bound theorem, you need to firstly try to predict the collapse mechanism. That means where is the location of the plastic hinges. Firstly, maybe we have a plastic hinge at point A. After formation of the first plastic hinge is still stable, you add another hinge, point C, right? After adding two hinges, just like a simply supported beam, then you can add one more. Insert one more hinge, maybe at point B. At this time, you see this unstable mechanism. It seems that the beam may have a large diffractions when the load increases a little. You may see this kind of large diffraction bending. So based on this kind of mechanism, you can use upper bound theorem to calculate the things again. Three hinges at point A, point B, and point C. Point A, assume the rotation here is theta. The rotation on the other side is also equal to theta because this is a similar triangle. Then what is the internal work? Internal work is equal to the plastic work at all plastic hinge. At point A, the plastic work is MP theta, because the moment at point A is MP. Plastic moment. The moment at point B and point C are also MP. The plastic work at point B is equal to MP 2 theta. The rotation of the plastic hinge at the middle is bigger, plus the plastic work at point C. The plastic hinge at point C is actually identical to the plastic work at point A. A and C are identical. So when you read the solution, I directly combine the effect of A and C together. So the total internal work is 4 MP theta. External work, I think we have considered this nature of external work many times in this PowerPoint. This is the third time, I think, right? Point low, you find out delta here. You can find out delta using uplink. I don't want to repeat again. This is delta. Okay, delta. This is the third time we saw this arrangement. Point low with delta. You can assume that there's a big circle here, and then you can calculate uplink. Uplink of a circle. Uplink of a circle is equal to S is equal to the radius times the rotation. So you have the energy equations. Once you have the energy equations, you can see that you have theta on both sides. Eliminate theta on both sides of the equation and put PC on one side of the equations. Then you have this answer, PC, equal to 8 MP over L. This is upper bound theorem, pretty easy if you understand the steps. There's no matrix, no differential equation, right? No cycle sign, relatively straightforward. That is upper bound theorem. What happens if we have a beam more complicated? It is also a one-span beam, but this time we have two concentrated loops at two different positions, point B and point C. In example 2, we have already considered this arrangement, one end fixed, one end roller. But in example 2, we have only one concentrated force. In this example, we have two concentric forces. Try to estimate the collapse load using upper bound figure. When you want to use upper bound figure, you need to estimate the collapse mechanism. That means you have to find out the position of the plastic hinges. Maybe I give you 1 minute, you can think about the collapse mechanism. Where are the position of plastic hinge and where are they? How many? How to estimate the number of plastic hinge required? If you remember, there are some different approaches. You may use the degree of indeterminacy. You can count the number of reactions minus the number of equations. You may calculate the numbers. Or maybe you can add the hinge continuously on the structure to see how many. Right? Say, for example, I arbitrarily add 1 hinge. Upon A, normally fixed end is more critical, right, for one span beam. After formation of 1 hinge, it's still stable. That means it's able to form 1 more hinge. Say, for example, point B. After formation of plastic hinge at point A and point B, it becomes unstable. You can see this kind of diffraction. What I want to mention is that it seems that 2 hinges will make the structure unstable. Okay, 2 hinges will make the structure unstable. But you may ask, hey, why is formed at point B? Why not point C? Actually, point C is also one possibility. The hinges may form at point A and point C. It will also give you this kind of unstable mechanism. Is there more options? Instead of point A, point B, point A, point C, instead of these 2 combinations, AB, AC, yeah, 1 more. In theory, the hinge may form at point B, right? In theory, also, although I think it's not possible, but in theory, the hinges may start to form at point B and then point C. You may also see this kind of unstable mechanism. What I want to mention is that the number of plastic hinge is still equal to 2. The number of hinges that make the structure collapse is still equal to 2. It will not affect by the loading. The number remains the same because the number of plastic hinge required depends only on the boundary conditions. Right? It's nothing to do with the loading. But the loading will affect the critical positions. In this example, it seems that we have 3 possibilities. So you have to apply upper bound figure 3 times for each scenario. If you find that there are more than 1 possibility, then you have to try all combinations and then use upper bound figure to find out the collapse load for all combinations. Finally, pick the minimum collapse load. Pick the minimum collapse load. That will be the collapse load of the structures. The smallest value, P minimum, is more critical, right? You can imagine that if the loading increases gradually from 0, the structure will firstly reach this minimum level. and then collapse. They cannot develop further. So this is the idea of this example 4. You have to try different combination. When we take a look on the solution, you can see that 2 plastic hinges are sufficient to make the structure collapse. So, but we have different combinations. So we have 3 combinations: AB, AC, and BC. You have to try all 3 combinations. Case 1. Case 1. I will show you the plastic hinge location. For case 1, we have plastic hinges at point A and point B. I assumed that the rotation at one end is theta. The other side, it is equal to 2 theta. Why we have this ratio? Actually, you can derive easily. You can ignore these 2 numbers. Assume that you don't know their values, okay, at the beginning. If you don't know their values, you can set one is theta, one is alpha, okay? This is delta. Delta is the displacement related to the point node, okay? Well, how to find out delta? According to our discussion, delta is equal to arc length, right? Arc length. This time there are 2 circles you may consider. You have a circle on the left. You have a circle on the left. You can also consider the circle on the right. Say, for example, let us consider the circle on the left first. On the left, if you want to express delta using the left-hand side circle, the value is equal to L over 3. I think the total length is L, right? This is the distance between AB is L over 3 times alpha. This is the expression obtained using the left-hand side circle. Similarly, you can express delta using the right-hand side circle, the bigger circle. And this time, the radius is longer, to L over 3. The angle is theta. So by using this relationship, you can find out the relationship between alpha and theta. Alpha is equal to 2 theta. So the trick is that you can set different angle at the beginning if you cannot realize their ratio. And then later on, you can consider some common displacement. Just like this example, we have one common displacement at point B. You can consider this common displacement and express this common displacement using 2 different circles, different angles. Finally, you can get the relationship. Okay, some tips for you. You will see this tip again in the next chapter. But anyway, so we have one side theta, one side 2 theta. Now we have to calculate our internal work and external work. Internal work, I think plastic work is more easy to calculate. So I talk about plastic work first. You have 2 plastic hinges, point A and point B. The plastic moment at point A is MP. The rotation at point A is equal to 2 theta. So MP 2 theta is the plastic work at point B. The plastic work at point B. Point B, you can see that point B is the member is originally a straight line. The member is originally a straight line, but now you can see that it's under a bending of 3 theta. So the plastic work for the second plastic hinge is MP 3 theta. Point D is not plastic hinge. Point D is a roller support, a real hinge. So there's no contribution from point D. Next, this is internal work. You have to also calculate external work. When you calculate external work, remember that there are two loadings here. There are two forces. There are two forces. When the beam bends in this manner, you can see that both force at point B and the force at point C will do works on the structure. They are work done due to the two concentrated force. So in this problem, we have to find out the corresponding displacement, delta 1, delta 2, and then multiply by the corresponding force. That will give you the total work done. Maybe I call this delta B. This is delta C. Suppose there's another force right here, PP. I think this time it's more convenient to consider the right-hand side circle. You can use arc length twice to calculate delta B and delta C. Delta B is equal to the radius 2L/3 times theta. So this one, oh, I highlighted the wrong one. This part is actually equal to delta B. 2L is the radius of this big circle, 2L/3, and then times theta. Give you the first displacement. Displacement times P give you the first work done. The second force also do some work, but the contribution is smaller because delta C is smaller. Delta C, you can use the work done equation again, or if you like, you may use similar triangle. The radius is L/3. The rotation is theta. So actually this is delta C. Similarly, you see thetas on both sides of the equation. You can eliminate theta on both sides of the equation. Cancel it. You can express the loading in terms of only the length and the plastic moment. PC, maybe you can call this PC1, case 1, is equal to 5 MP/L. This is the answer for the first case. We have to redo the same thing again for case 2 and case 3. Same principle. You have to apply the same principle for case 2 and case 3. The procedure is quite similar. Say for example, when you consider case 2, the plastic hinges form at point A and point C. You can set up the corresponding rotation property, theta here, 2 theta on the other side, just opposite, right? Just reverse. And then you can calculate the plastic work first, the plastic work at point A and the plastic work at point C. You can see that the plastic work at point A is smaller as compared with the previous case. The rotation is only equal to theta. And then you calculate the two delta B and delta C again. Same technique. Find out delta B and delta C. Equate the external work and internal work together. Then you can find out our collapse law. The collapse law for case 2 is equal to 4 MP/L. It seems that this one is more critical. At this moment because it's smaller. The last one, case 3. Case 3, plastic hinge form at point B and point C. So this is the corresponding configuration. Point A is fixed end. And also, we ignore our elastic deformation. If you ignore the elastic deformation here, just a horizontal portion, there's no any bending because you ignore the elastic component. So it becomes a horizontal line between A and B. The deformation only occurred between BC and CD. When you take a look on this deformation shape, it seems that it's not realistic, right? So that's why at the beginning, I think that this is not quite possible. But in theory, you may have hinges at point B and point C. So we will do the analysis for this not very critical scenario. This one is more easy because if one side is theta, the other side is also theta because they have the same length, a similar triangle. So this one I think is even more easier in terms of calculations. You can calculate the work done, internal work and external work. And this one, we have two forces at point B and point C. We have two forces at point B and point C. You can see that the force at point B has no any displacement. This one has no any vertical displacement. So in this problem, only the loading at point C do some work on the structures. Delta B is 0 because we have only one term on the left-hand side, only one force do work. So after we arrange the equation, you can see that the corresponding collapse load for this failure mode is 9 MP over L. Large value. Large value means it's not very possible to occur. So along the whole analysis, you can compare PC1, PC2, and PC3. And it seems that PC2 most likely to occur. That means scenario 2 should be our realistic failure mode. Hinges form at point A and point C. You can think in this way: when the loading increases gradually, when the loading P increases gradually from 0, it will firstly reach the second collapse load. After reaching this collapse load, it will collapse. It cannot increase further to 5 MP or 9 MP. So this is our scenario. If you know the failure mechanism, once you know the loads, you can do analysis. You can do structure analysis to find out the remaining reaction, internal force, whatever, for your design purpose. Okay. But in this module, we mainly focus on how to calculate the collapse load, not the following process. In theory, if you know the collapse load, you can do the calculation further to find out the reaction, find out the internal moment, internal force at any cross section for design purpose. But in this module, we are not going to do so. We just focus on the calculation of collapse load P. I think that's sufficient for this module. The last part of this section is just some supplement informations. In the previous two sections, we considered one span beam under only concentrated force. Under concentrated force, you can evaluate the work done easily, right? Because for a beam under point force, you can find out work done simply using the product of force and displacement. But what happens if the beam is under uniformly distributed loading? In this section, I would like to give you some tips on how to calculate UDL in case if you want to use upper bound figure. Using upper bound figure, mechanism method means upper bound figure. Mechanism method means upper bound figure. When you use upper bound figure, dealing with distributed force, sometimes it's quite difficult for you to calculate the internal, external work. Right here, I would like to use one example to demonstrate how you can dealing with the calculations with UDL, one very simple scenario. Suppose we have fixed end beam under UDL. Try to use upper bound figure to estimate the collapse load W. This relies on some understanding of mechanics. How to calculate work for a beam under uniformly distributed under UDL. Fixed end beam. For fixed end beam, there are 3 plastic hinge form before collapse. Okay, 1, 2, 3. For fixed end beam, the number of hinges is equal to 3. 2 on the two sides. The last one at the middle. At the middle, because the beam is symmetrical beam. Otherwise, it will be somewhere else. But the beam is symmetrical, so we believe that the last hinge will form at the middle. 3 hinges. To calculate the internal work, I think internal work is pretty easy because internal work is nothing to do with the UDL. Internal work, you just count the rotation feet here, 2 feet at the hinge, at the middle hinge, feet on the right. In total, 4 feet rotation. 4 feet times velocity movement, MP, give you the internal work. Internal work calculation is quite straightforward. Just depends on the location of hinge, depends on the rotation, nothing to do with the loading. But what about the external work? External work, this time you have to calculate the external work due to W, due to the UDL. How to do so? You may start to consider one small element, maybe here. You consider one small element with length equal to dx. Maybe I draw this here. The length is dx. Under UDL. For a small segment under UDLW, you may convert this force to an equivalent concentrated force. The equivalent concentrated force is equal to W times dx. W times dx is the total force along this small element. Okay? Then what is the displacement? What is the displacement over here for this small element? Maybe I call this delta again. You can use arc length, right? You can use arc length. The radius. Maybe I call this x. The radius of this circle is x. The rotation is theta. The rotation is theta. So the work done for this small element is equal to the force, W dx, times the corresponding rotation, x theta. The corresponding displacement, x theta. This is the work done for one small element. You can integrate the whole things from 0 to the middle of the beam. We consider 1/2 of the portions and then double the values. It becomes the total work done of the system. Okay? It's testing your skill to doing integrations. If you trust me, then this is the answer. Okay? WL squared theta over 4. Testing your integration skills. Equate the two things together, then you can find that W, critical W, is equal to 16 MP over L squared. So you can, when you handle this kind of UDL using upper bound theorem, when you calculate the external work, you may start from element level. You consider one small element and then integrate the whole things to get the external work. This is one method. Integrations. There is another way. I think it's more straightforward. The other thing is that I directly consider 1/2 of the structures because of the symmetrical arrangement. For this 1/2 of the structures is under UDL. Using the same theory, you can replace UDL by one equivalent concentrated force acting at the middle of this UDL. Okay? You can replace UDL using the equivalent concentrated force. Actually, we used that same concept in the previous part. The distance here is equal to L over 4. Now, you can see that the force, the concentrated force, is equal to WL over 2. The corresponding displacement here, delta. Delta is equal to L over 4 times theta. Now you can ignore the UDL. You can ignore the UDL. Just treat this as a concentrated force. Concentrated force times delta give you external work. Same numbers. So you can calculate external work by considering equivalent polynomials, if you like. Just see which one is more comfortable from your point of view. You may use integration, or you may convert UTL to equivalent point force, and then treat this as a point force. Point force times displacement give you work done. So the end of chapter 11. In chapter 11, I firstly demonstrate the difference between upper bound fiber and lower bound fiber. In this chapter, we mainly consider one span beam with different boundary conditions. Pin end roller, fixed end, and then the last one is fixed end roller, something like that. We consider one span beam in this chapter 11. In the next chapter, we will extend the problem to continuous beam. Okay. Before that, we will take a short break.